Sum reduction today. The problem is that we essentially want to compute the sum of a given array. So the way we would do this in a normal CPU serial implementation is we would iterate over the array. Let's say this is the n-sized array. We would iterate over the array and keep a sum variable. And each time we encounter an element, we add that element's value to the sum and iterate over the entire array. So we have a order of n serial reduction. But for a parallel implementation, we have the opportunity for massive speed up because let's say we have enough compute power, enough threads in our system, and each thread can be responsible for maybe one element. So we can assign n threads, n by 2 in the first iteration. We can assign n by 2 threads, and each thread computes the sum of two elements and forms from array of size n. We have a array of size n by 2, which contains the each element contains the sum of two elements. In iteration 2, we do the same to get an array of size n by 4, and so on. So in total k iterations, we go from n to n par 2 by n divided by 2 par k elements. And let's say we want to find how many iterations it will take to finally get the summation of the entire array. That'll be n k is equal to log n. So we need these many iterations to reduce the array to just one element. However, the challenge with this implementation is, first of all, when n is very large. Okay, let's discuss this after discussing the first implementation. And note that while in this case I'm discussing parallel sum reduction, this same technique applies to any sort of a associative operation, like which follows the pattern like a sum operator b sum operator c give the same answer as a sum operator b operator c. So addition is such operation where a plus b plus c is equal to a plus b plus c. Similarly, multiplication is one operation. Similarly, what else? Addition. Max is one such operation. Min is such operation. So for all of these operations, the same technique that we'll be discussing today applies. So the first naive kernel would be we have we just do everything in global memory, that is the GPU DRAM, and let's say we have n elements, and let's say n is less than the maximum grid size supported by our hardware. What this means is we can assign each thread of our grid to one element like of the array. So let's say thread 0 maps to element, if this is one based indexing, thread 0 maps to 1, uh, thread 1 maps to 2, thread 2 maps to 3, and so on, and thread n maps to element n. In the first iteration, we thread 0 will be responsible for calculating these two element sum, thread 2 will be responsible for calculating these two sum, and so on. And iteration 2, thread 0 will be responsible for reducing basically this whole subarray. Thread 4 will be responsible for getting the partial sum of this, and so on. So we'll have k such iterations again. Yeah. So this is the pseudocode for this implementation. But the problem with this is, first of all, we assume that n should be less than max grid size, which is obviously not always the case because grid size is limited, whereas n we can have n of the order of 10 power 9 sometimes also. So this is clearly a very huge bottleneck. And also a problem is too many redundant global memory, right? So you can see that here, let's consider this location like out 0. So in iteration 0, we write here. Iteration 1, we again write here. Iteration 2, we again write here. And iteration k, we again write here. So at a single memory location, we can have maximum k writes, k global memory writes, which is of course not ideal because global memory writes are kind of expensive. So now just let's go back to our discussion here. So for parallel sum reduction, when n is greater than the grid size supported by the hardware, we need multiple thread blocks, and we can. So the idea is we assign each thread block to reduce a certain sub part of the array. Let's call that subarray. So we assign each thread block to reduce the a certain subarray to one value, and each thread block will reduce a portion of the array to one value, and then we need to basically communicate the partial results between thread blocks, and then we need to reduce the partial results into a final accumulated full array sum, reduced sum. So note that here we need synchronization between thread blocks because we need to communicate the partial results between thread blocks. So this is where we need to use kernel decomposition. So by kernel decomposition, I mean, um, let's say we have n elements here. In the first kernel decomposes from n to n by 2 elements, n by 2 elements. Second kernel reduces from n by 2 elements to n by 4 elements, and similarly, the kth kernel finally reduces to one element, which is our answer. And after each kernel invocation call, we have uh, an implicit synchronization of all the results. So after each kernel call, we are sure that all of these results are synchronized. Like they are when, for example, when after kernel 1 is called, when kernel 2 is called, we are sure that the values here are correct. Okay, so this is the key idea that each kernel launch serves as a global synchronization point. So using each kernel call, we can do global synchronization, which is not supported by CUDA like explicitly. So in the second implementation, we use shared memory. Uh, so we use the same idea that we discussed, where each block um, reduces a certain portion of the array into the sum of that subarray, and then we use multiple kernel calls. So the way it looks in code is the code is essentially the same, where instead of out of I, we have shared memory location of corresponding to that particular thread, and we also add from something like this. But I is the index within the thread block. Okay. So this is what is happening. First of all, loads each thread loads its corresponding element into shared memory here, and then it's essentially the same where we calculate where. So I here would be um, this just thread id dot x, and this would be for s is 1 to s less than block dimension dot x. I out of I is enough. Basically this is shared memory of, and so first I is thread id dot x, and then we load. So shared memory of I is equal to in of global, that is block id dot x into block dim dot x plus tid dot x. So it loads the global data into shared memory, and then we use shared memory of I is equal to shared memory of I plus shared memory of I plus S in this implementation. Okay, and finally, after all of these, after this block, after the first iteration of block, we let's say this block has size 1024. After first iteration, we see that from 1024 we'll have 512. In the second iteration, we'll have 512 to 256, and so on. And finally, we'll have when s, this is like when s is equal to 1, this is s is equal to 2, and finally when s is equal to, I think, like 9 or 10, s is equal to 10, we have just one element. So once we have the entire for loop done, we have this additional condition where we store to global memory, because when we call the second kernel, we'll read this value, right? Kernel 2 will read this value. So this is where we store the entire thread blocks reduced sum into global memory. Okay. But the problem with this kernel is warp divergence. And so there are two issues basically. First, let's talk about the second issue, where we discussed about kernel launch, multiple kernel launches, right? Because we need global synchronization. But the problem with this is every time we call a new kernel, there is a GPU to CPU memory transfer. So when we call kernel 1, initially the data was in CPU. When we call kernel 2, kernel 1, it is first copied to the GPU. Kernel 1 does some computation, and then we transfer the data back to CPU. Then kernel 2, when we call kernel 2, there's a CPU to GPU memory transfer. Kernel 2 does some computation. Kernel 2 stores in CPU, and then so on. Kernel 3 reads data. So there's a CPU to GPU memory transfer. Kernel 3 does some computation on GPU, stores back data back to CPU, and then we have kernel 4, and so on. So for each kernel, we have a CPU to GPU and GPU to CPU memory transfer, which is kind of expensive. This is one small issue, and the second issue is warp divergence. Why I say there's an issue of warp divergence is because in the first iteration everything is good. Like in the 0th iteration, when we are loading the each thread loads one element into shared memory, that's good. But in the first iteration, you see that thread 0 reduces from element 0, calculates 0 and 1. Thread 2 calculates elements 2 plus 3. Thread 3 calculates 4 plus 5, and so on. So we see that only in iteration 0, in iteration 1, only the sorry, this should be thread 4. Only the even thread indices are active, and odd thread indices are inactive. So if you recall that, why is it taking so much time? Okay, recall that in the way a warp executes is in lockstep. So if we have warp size of 32, and if we have a warp size of 32, all 32 threads in a warp will execute the same instruction. If there is a branching condition where, let's say for example, in this case all even threads execute one instruction and all odd threads execute one instruction, the warp execution, instead of happening in just one step, it will happen in two steps, where for this condition only the even indices will be active, and for the second run only the odd indices will be active. So basically it takes double the time for this warp to execute, so which is a problem. And the way we overcome this is by changing how the work is distributed between threads. So the reason for warp divergence was that some threads were doing work and some threads were not doing any work. We want that consecutive threads, thread 1, should all do work, and then maybe consecutive last few threads should not do work. We want something like this, whereas here it was like thread 1 does work, Thread 0 does work, thread 1 does not do work, thread 2 does work, thread 3 does not do work. So this is not a good like this is not a good execution way when we are trying to avoid warp divergence. So the way we do this is, instead of assigning, earlier we had thread 0 to compute this and thread 2 computed this, right? We just assign thread 1 to compute this, thread 2 to compute this, and so on. So the change in code is only this, where um, we don't filter by um, basically thread index. We calculate the index each thread is responsible for and do the reduction. Okay, but the problem with this is shared memory bank conflicts. The reason is, let's say we have, let's discuss what bank, how shared memory is stored. I mean, elements are stored in shared memory. So shared memory has 32 banks, and consecutive memory locations are stored in consecutive banks. So let's say we have an array of, in shared memory we have an array of size 64. Element 0 will be stored here, element 1 will be stored here, element 31 will be stored here, and then again element 32 will be stored here, 33 will be stored here, and so on till element 63 will be stored here. So every time we try to access a warp, let's say we are trying to access, uh, let's say we have a warp where thread 0 accesses thread 0 accesses element 0, thread 1 element 1, and thread 31 element 31. Instead of, we can just in one read from this shared memory, we can read all of these, each we can read values from these separate banks in parallel. So that is the power that this bank arrangement gives us, where if we have 32, uh, like in a warp we have 32 threads and each thread reads from a different bank, we can read all the 32 values from each bank in parallel. So this is the power that banks, like the storage method of the way that elements are stored in shared memory in different 32 banks, it gives us this power. But the problem with our current way in which we access data from the shared memory is that, let's say in iteration, this is iteration 0, right? Let's talk about, this is iteration 1, right? So in iteration 0, we just are loading things from, each thread loads one element from global memory to shared memory. So in iteration 0, we have thread 0 loading element 0 into shared memory, thread 1 loading element 1, and thread 31 loading element 31. Let's talk about a warp, one warp. And we know that element 0 will be stored in bank 0, element 1 in bank 1, element 31 in bank 31. So since each thread accesses is trying to store in the shared memory in a different bank, we have no bank conflict because we just need one write to the shared memory. However, in iteration 1, thread 0 is trying to store in shared memory because of this, like thread 0 is trying to is trying to store in shared memory 0 location. Thread 1 is trying to store an element in shared memory 0 1 0 1 2 3 4. In shared memory 2 location, thread 2 is trying to store in shared memory 4 location. So this is what is happening. So let's consider a warp of 32 threads where we have T0 to T31. So T0 accesses bank 0, T1 accesses bank 2, and um, T0 bank 2, T1, T0 bank 0, T1 bank 2, T15 accesses bank 30, T16 accesses bank 0 again, and T31 accesses uh, T0. 30. Oh, so there should bank 31 also. T30 31 accesses bank 31. So we can see that bank 0 is accessed twice, bank 2 is accessed twice, and bank 30 is accessed twice. So this is a two-way bank conflict because to read when T0 to T31 try to read their or sorry write their values to shared memory, there'll be in first write there'll be writes to bank 0 to bank 31, and then we need another write to write again to bank 0 to bank 30. So this is a problem because we have a two-way bank conflict, and this problem becomes worse in iteration 2, for example, because um, we have a four-way bank conflict in iteration 2. And the root cause for this bank conflict is because consecutive threads are not operating on consecutive data locations in shared memory. Because in iteration 2, for example, thread 0 is operating on bank 0 or uh, on data location 0, whereas thread 1 is operating on data location 4, which has a stride like a difference of 4, right? So this is a problem. If we can somehow change the way consecutive threads are loading, storing values to to locations in shared memory, such that consecutive threads load store data from or to consecutive locations in the shared memory, then we'll be able to avoid these bank conflicts. So the fourth implementation we'll be discussing does exactly this, where thread 0 thread 0 will in iteration 1 thread 0 reduces value calculates the sum of this and this. Thread 1 calculates the sum of this and this. So you can see that consecutive threads, thread 0 and thread 1, access consecutive locations in shared memory. So this way we are able to reduce the number of bank conflicts to 0. So this is the code for this. Did we have code? Okay, this is the code for this. And so after doing this, we are able to eliminate all bank conflicts. But an observation here is that um, after each iteration, we have a sync threads command. And the reason we have a sync threads command is after each iteration, we want all the threads, all the shared memory locations to have the we want to be sure that each shared memory location has the sum that it is supposed to have before moving on to the next iteration, because in the next iteration we are accessing data from those shared memory locations. So before we move on to the next iteration, we need to be sure that each shared memory location has the sum of values it is supposed to have. However, note that once in this code, let's say we have a stride of 32 in iteration, let's say 4 or 5. Let's say in this code we have s is equal to 32 here. So we do not need to do a sync threads after we have s is equal to 32, because um, shared memory tid x plus equal to shared memory tid x plus s, because consecutive um, okay, when s is equal to 32, we have basically 32, let's say the when s is equal to 32, we have data here and data here. We need in this iteration when s is equal to 32, we have a reduction from 64 elements to 32 elements. But we use just 32 threads. So that is, we just use one warp of threads. And recall that when one warp executes, a warp always executes in lockstep. So each thread 0 calculates the sum of this and this, right? And thread 1 calculates the sum of this and this, and thread 2 calculates the sum of this and this. So we can be sure that all of, like, this purple thread, this white thread, and this blue thread, we can be sure that all of these operations happen in parallel, so that after all of these operations happen, when we go from 64 elements to 32 elements, we do not need any synchronization between threads, because this is when operations happen within threads in a warp, there is implicit synchronization because a warp executes in lockstep. So we do not need these sync thread commands. So this is an opportunity for us to do further optimization. So for when s is less than or equal to 32, there is no synchronization required because all threads in warp by default run in lockstep. So we, instead of uh, initially this loop was still here. So from s is equal to 1, we change the loop to s is equal to 32, greater than 32, and then we insert this code where we like, if thread id x is less than 32, that is for warp 0 in the entire block. Let's say there are 1024 threads in a block. So after this loop runs, we have 64 elements which need to be reduced, whereas the s is equal to 32. So after this loop, we call warp reduce, like each of these threads call the function warp reduce, where in the first command, which is this command, we each thread calculates the sum of this plus this. So after this command, we are able to reduce from 64 elements to 32 elements. Like 32 elements contain the entire sum. For when this command is executed, we are able to reduce from 32 elements to 16 elements. Um, Actually, we're able to reduce from 32 to 16 elements. But note that all of these threads are executing this. So these threads contain the correct value, but these threads also will do the reduction of this plus this. But we do not care about these values. We just care about these values. So after doing all of these reductions, all of these operations, like basically we unrolled the last few iterations of this for loop, because we do not need to, we wish to not use sync threads. So after doing all of this, finally shared memory 0 will have our desired answer, like the reduction of the entire 1024 thread block. And a final approach that we will be discussing here is thread coercioning, where initially, like till now, we were discussing if n is equal to 1024 times 1024, we would, and let's say block size is 1024, we would, so from n is equal to 1024, we'll call a kernel where each block gives us a one answer. So from n is equal to 1024, we'll have n is equal to 1024. From n is equal to 1024 square number of elements initially. After calling kernel 1, we'll have n is equal to 1024 elements. And after calling kernel 2, we'll have just n is equal to 1 element, which has our answer. So rather than doing this two steps, what if we assign each thread to do more computation, like more loads, such that each thread does 1024 loads now. If each thread does 1024 loads and we have 1024 threads, So in just one kernel call, we'll be able to reduce 1024 times 1024 elements into just one element. So we'll be able to save one kernel call. This might be a good thing or a bad thing depending on how well we are executing the hardware resources. So, for example, let's say in this case, let's say consider this case. Okay, let's discuss. For example, let's say we have access to NVIDIA 100 GPU, where number of SMs is 108, max WOPs per SM supported is 64. Let's say we design our grid structure such that the block size is 1024. So, according to these specs, the number of blocks resident on a given SM would be 2 because 64 is the max number of warps per SM, 32 is the number of threads per warp, and block size is 1024, right? So this is like 2 blocks can be resident per SM. And since we have number of SMs is equal to 108, number of blocks at one time that can run on the hardware NVIDIA 100 is 216 blocks. So if this is our hardware and our case is that we have n is equal to 1024 square number of elements, um, if this is the case, in kernel 1 we can have 1024 we have 1024 blocks, right, out of which 216 will be executed in parallel. So we'll have to do like 5 serial calls in hardware to execute kernel 1. Okay, so basically we have 5 times utilization of hardware. However, if we did thread coercioning, if we did thread coercioning where each block corresponds, each block calculates 1024, does 1024 loads, we'll have just one block per grid. And although the hardware supports 216 blocks uh, at one time, since we just have one block, uh, like since we just have one block in our data, we are not at all utilizing the hardware effectively because we are losing out on 206 times parallelization. So in this case, when n is equal to 1024 square, using thread coercioning is not a good idea. However, if we have, for example, n is equal to 1024 times 1024 into 216 number of elements, when we call kernel 1, since each block has 1024 threads, and at a time number of blocks supported is 216, there is still a 1024 times serialization hardware that is required. Whereas if we do a thread coercioning where each thread loads 1024 elements, since each since the number of blocks supported by hardware is 216 and each block has 1024 threads, there is no serialization in hardware, right? Because the hardware resources are utilized, like there is just one time all the hardware, like all the data will be able to get stored, will be able to utilize the hardware effectively in just one iteration, and then we'll have kernel 1 execution done and then we'll have kernel 2 execution done. Whereas in this case, first all of in first iteration all of the hardware resources are utilized perfectly. Then we'll have to load the next out of these 1024, since there are 1024 blocks, 1024 into 216 blocks, and each at one time 216 blocks can be scheduled on the hardware. In first iteration, 102 216 blocks are executed on the hardware in parallel. In second iteration, next 216, and in the last of the 1024 iteration, the next 216 blocks are executed. So there's a serialization of um, like block scheduling that is happening. So both of them can be good, but in this example, we might want to check out this, because first of all, we are saving out on one kernel call and avoiding one GPU to CPU memory transfer. And also, there's some overhead associated whenever we are launching blocks. So this is called a serialization, hardware serialization overhead, which we are suffering over here, but we're not suffering over here. So for this case, this approach might be like thread coarsening approach might be worth a try. So these were all of the approaches we have. We can try all of these, and we try to iteratively improve on the runtime. Uh, yeah, for the parallel sum reduction. Thank you.